Hello, and thank you for tuning in to my talk. I'm Paul Rosen from the University of South Florida, and this work was done in collaboration with my PhD student, Ghulam Jalani Quadri. When visualizing data with line charts, as the data becomes large, it can get cluttered and noisy, making analysis difficult. For example, if I ask you, what are the most significant peaks in this data, you may have a hard time deciding which are truly important. To improve the presentation of the data, we can turn to data smoothing. However, in doing a quick search of the available smoothing methods, you'll discover there are many options available. Importantly, while the output of the techniques looks similar, each preserves different properties of the data. If we again ask, what are the most significant peaks? Your answer will vary greatly depending upon the smoothing method chosen. And so this leads us to two natural questions about smoothing. First, which smoothing method should I choose? And second, does it even matter which smoothing method I choose? Today I hope to answer those questions for you. Up until now, the visualization community has lacked a work analyzing and classifying line chart smoothing methods. For this work, we hypothesized that the effectiveness of each smoothing technique depends upon two factors. The first factor is the nature of the data being smoothed. For example, the data may have long-term trends, cyclical behaviors, or high-frequency spikes that influence the smoothing results. The second factor is the set of visual analytics tasks that will be applied to the data. This work has the following contributions. First, we devise a taxonomy of 4 classes of line chart smoothing. I won't be discussing this taxonomy today, so please see our paper for details. Second, we construct an analytical framework for measuring the effectiveness of smoothing techniques under 8 different low-level visual analytics tasks. Third, we provide a method for ranking the effectiveness of various smoothing methods. And finally, we evaluate 12 smoothing methods across 80 datasets from 13 different categories. Let's begin by discussing the visual analytics tasks we consider. We selected a set of low-level tasks performed on line charts based upon Amar et al.'s low-level task taxonomy. We selected 8 visual analytics tasks, as seen here. Those include retrieving a value, which has the user estimate a specific value in the data. Determining the range, which has the user estimate the range of a specific set of values. Computing a derived value, which asks the user to perform an aggregation task, such as determining the average value. Finding extrema, which has the user identify peaks or valleys in the data. Finding anomalies, which has the user identify points that disrupt a trend. Characterizing a distribution, which has the user summarize a trend in the data. Sorting, which has the user order data by their relative values. And finally, clustering trends or points, which has the user grouping similar data together. We further group these tasks and devise analytical measures of the effectiveness of each. For example, the retrieve value and determine range tasks, we identified a measure we called total variation. Total variation uses the L1 and L infinity vector norms to measure the effectiveness. For the find extrema and find anomalies tasks, we measure the variation in the peaks and the valleys in the data. This is found using the Wasserstein and bottleneck distances of the critical points. For the compute-derived value task, we use a measure of area preservation, which is the difference in the integrals of the input and smooth data. For the characterized distribution and clustering trends task, we use a measure called frequency preservation, which is an L2 norm of the frequency domain. Finally, for the sorting and clustering points tasks, we use a measure that we call value order preservation, which is based upon Pearson and Spearman correlations of the input and output data. You'll find the details of how all of these measures are calculated within our paper. Once our metrics were defined, we set about a method of comparing the effectiveness of different techniques. To do this, we devised a method for ranking the efficacy of methods either at a single level of smoothing for a single dataset, across all levels of smoothing for a single dataset, or across multiple datasets simultaneously. The resulting rankings are represented in a rank plot as seen to the right, where better ranked techniques appear towards the top. In this particular example, we rank the effectiveness of techniques across all smoothing levels for 6 individual datasets, and the overall performance for all 6 datasets. Once again, please see our paper for details about this calculation. Finally, we evaluate 12 commonly used smoothing methods as seen to the left. Using 80 datasets grouped into 13 categories with examples to the right. We evaluate these methods and data across all visual analytics tasks that I mentioned earlier. I'll now discuss some specific results, in this case for the retrieve value and determine range tasks. The overall best performing method was Gaussian smoothing. However, it wasn't the best method for all data. It tended to do best with data that had long-term or cyclical trends within it, as seen to the left. The second best method was topology-based smoothing, which tended to perform best on data with spiky features, as seen in the highlighted datasets to the left. Finally, the third best method overall was Savitsky-Golay, which performed best only with a single specific data type, that being the EEG data that we tested against. Here we see another example for the task of computing a derived value. This task had a single universal winner, which was the low-pass cutoff filter. It performed the best on all data types tested. The second best method overall was the topology-based smoothing, which performed second best for all except 2 datasets. Of course, these examples have covered just 3 of the 8 tasks that we analyzed. The remaining are, of course, enumerated in our paper. To better inform visualization design decisions, we also provide an overall grade for all 12 methods for each of the 8 tasks. The methods essentially fell into 3 groups: those which are good in general, those which are good for specific tasks, and those which should be avoided in most cases. In terms of overall good performers, we found that Gaussian smoothing performed admirably for data, in particular with long-term or cyclical trends, while the topology-based method performed particularly well on data with spiky features across all tasks. Nevertheless, either of these methods, in general, is a good default choice. We also identified a few methods, including Savitsky-Golay, low-pass cutoff filters, and the Douglas-Peucker method that performed well for specific tasks, often better than the Gaussian or topology-based smoothing on the same task. For example, with the find extrema and find anomalies tasks, the Douglas-Peucker method was the single most effective technique. Therefore, if this task is critical to your analysis, using Douglas-Peucker should be considered. Finally, we identified 7 methods that rarely performed well, indicating that they should only be used if you have a very specific reason to do so, perhaps having to do with the features of focus in the data or the high-level analytical task being performed. Of particular note in this group is uniform subsampling, which is a commonly used data reduction method, also commonly used for its smoothing side effects. Our results show that using it for smoothing is ill-advised, as it produced unreliable results that preserve no particular feature of the data. In conclusion, through building and testing our framework, we did find that no single smoothing technique was ideal for all types of data or all visual analytics tasks. Furthermore, we note that the choice of smoothing methods can have a significant impact on how data are distorted, and thus how they may be perceived by an end user. For the best results in your visualization, our framework can be used to analyze and select the most effective smoothing method for your specific dataset and tasks. However, if that isn't an option, you can at least use our findings to make a reasonable choice of which method to use for your specific scenario. To view a demo of our framework, please see the link to the right. I'd like to thank you for your attention. To the right, you'll find links to our code, data, and paper, and I would be happy to take any questions.